Hi, everyone. Hopefully, you're enjoying the conference so far. Let's talk about secure coding of industrial control systems. My name is Vivek Ponnada, and I have all my work life worked in industrial control systems, and I've been doing ICS operations technology cybersecurity for the past 8+ years. I've been a field engineer, sales and service manager, did business development, and I'm currently in a services role covering customers in industrials from coast to coast in Canada. Thanks to the nature of my job, I've worked in several countries. I have an engineering degree, an MBA in finance. I also have an industrial controls cert from SANS. Here's my contact info. And this is today's agenda. We'll talk about the industrial control systems. What does coding mean in ICS? And we'll specifically discuss the top 20 secure PLC coding practices project, the list with some examples. So what are industrial control systems? So you'll hear these terms, programmable logic controllers, or distributed control systems, or supervisory control and data acquisition. So PLC, DCS, and SCADA. They're different types of control systems meant for operations in power plants or refineries or oil pipelines, but also in the transportation sector, healthcare, for example, building management systems. They use a lot of these similar technologies. And in the Purdue reference model, they're at the level 1, and historically they were not built with security in mind. So there was no encryption, hardly any authentication. So PLCs, if you just Google the term and people talk about how insecure they are. In fact, they're talked about as insecure by design. And here's how they look. So this is a system where around this area you got the PLC itself, the controller CPU, and then you have the I/O modules, input-output modules that process the signals coming from the field, and those are terminated here. So the sensors from the field that collect information about temperature or pressure, or one that controls the valve, or some kind of motor start stop, all those inputs and outputs are wired here to these green terminal blocks, and the information goes to these I/O modules for processing. And you have maybe a comms or some kind of power distribution system here, and you get the power from top here. I also show a little bit specialized equipment like the barriers for intrinsically safe areas, but this is not the focus of today's discussion. But in general, this is an example of how a PLC is seen in the field. And how do we code these ICS systems? We have IEC 61131-3 that outlines the different languages that are used for coding or programming these programmable logic controllers. Ladder logic by far would be the most popular, but we also have function block diagrams, instruction lists that are now deprecated, structured text, and sequential function charts. We'll go through some examples. So ladder logic, this is how it looks like. As you can see, it looks like a ladder that we might use at home. In this, you read this from left to the right. So you have two operational paths. So you can manually start the motor. Maybe it's a push button or a lever or something like that. Or you have these two switches that are operated by an operator or something else from another part of the logic. So if you have the switch 1 on and switch 2 on, then that enables the motor to start automatically, or you start this manually. In this function block diagrams, you see this kind of structure where you got the inputs from the left coming in. There's an operation going on here, a division maybe, another section, with inputs coming in with maybe a multiplication here, or any operation for that matter. And then these two go to this other block. So you can visualize what's going on a little bit differently from how you visualize that in this ladder logic, but the end result is the same. Essentially, it could be this motor that we're talking about here that is coming on, just like what we're experiencing here. We also have instruction lists that if you had access to registry and you're programming that directly, you might then, say load A as a value, add this value B, and then do something else with it, and so on and so forth. Structured text looks more like a basic or some kind of relatively modern programming language, where you can then use statements like if or else, and build a logic essentially. The purpose doesn't change. Whatever we do, whatever language you use, in this example, we might be starting or stopping a motor. And then we also have sequential function charts. These are used when the complex, the logic is more complex, and you kind of lay out, how it's working and what's going on in that, in the whole plan, for example. Now, like I mentioned before, coding of these programmable logic controllers was never done with security in mind. So a couple of years ago at a security conference called S4, one of the presenters, Jake Brodsky, highlighted some things that we could do with these PLC programming that some people were doing, or many people were doing in some instances, but not really codified anywhere. So his presentation kind of focused on things that we could still do to improve the coding of PLCs with security in mind. So after that, a couple other volunteers started this project. They named it the Top 20 Secure PLC Coding Practices, kind of like what we have in the IT world, right? Top 20, IT best practices. Similarly, they started this project. Nearly 1,000 people registered on the website as contributors, and after about a year or so of multiple meetings and discussions later, we have the list ready now. It's published here. It's free to download, and you can use it for any purposes as you see fit, because these are all best practices coming from the experts. In many cases, people have known some of these or maybe some version of these, but they haven't necessarily looked at it with security in mind. Maybe there were some maintenance benefits and that's why they did something, but now we're trying to explain why it's good for security as well. So let's look at the list. Here's a list of 20 practices. We're not going to talk in detail about all of them, but we'll go through a couple of examples so you can kind of understand, the rationale behind these individual practices. So first up, let's take integrity of either I/O or code. And in this example, let's use these three sub-examples. So one, the practice itself is called validate inputs based on physical possibility. So let's take this first section where, let's say there is a piece of code where you have these inputs coming in, and it's supposed to take 5 seconds for a gate to open. And then you have an output that shows, hey, the gate is open. And then maybe you have another for water control, and because the gate is open and the water is available, maybe you do something with it. Right? But let's say the gate did not open in 5 seconds and it took 10 seconds. You have to alert that. And that's good because it's got maintenance advantages. You know that something is wrong with the gate itself, or maybe there's some malfunction in the actuator or something like that. Or it could be a malicious attacker doing something with the inputs, and that's why the gate is now taking more time to open, right? Or the opposite. Let's say the gate normally takes 5 seconds to open, but you have an indication that it opened in 2 seconds. Again, you have to alert that because it could be something wrong, right? Both in the physical equipment itself, or someone messing with the packets on the network, on this low-level network for that purpose. Similarly, if you have a repeating activity, something that happens during the day and at night, but suddenly that activity that's supposed to happen at night is happening during the day, right? You have to alert that. And then finally, this limit operator entry for set points to what's practical and physically possible. Let's use the same function block example. Let's say the operator can enter a value here of 10, for whatever that 10 might be, but physically in the process, there is no 10. Let's say the limit of how much a tank can drain in a certain time, or how much a valve can open in a certain time period. is half of that, then what's the point in allowing the operator to be able to enter 10, right? All that does is it creates another attack vector so that you either maximize this, causing other problems, right, where this will get stuck at the maximum value, or the process will take a long time to come back to the normal condition from the maxed out situation. So you want to limit that. So this practice essentially highlights the reasons with some examples of why you should validate inputs based on the physical plausibility of those events to happen. Next up, we have this other example, another practice for tracking operating modes. Let's go back to the picture that we saw before. So in this PLC system, so you see this key here. Most PLCs have this. This key, you can put that in the run mode for letting the controller do its thing for normal process operation, but you switch it to a program mode for allowing the engineer to download code to the controller. Oftentimes you see that this key is left in the program mode, and the reason being then the engineer doesn't necessarily have to be present here locally and connect with this controller to download code. He might be able to just download code from an engineering workstation on the network somewhere away in a safe zone. So this might be in a hazardous zone. This might be out there where the engineer needs a permit, needs to put on his coveralls and hard hat and safety boots, and put himself at some level of physical risk to access this controller versus being able to download code from a remote location that's safer. However, the downside is that's an attack vector. So a couple of years ago, we had a situation in the industry where Triton is the name of that attack. Someone tried to program safety PLCs from remote and use it as a vector to disrupt operations in that particular plant in Saudi Arabia. So our practice is monitor this, have an alert, and there might be legitimate reasons why this is in program mode. But after 8 hours or so, and no one is working on it, you shouldn't be in program mode, so that alert should pop back up. So that way the operator that's available 24/7 always has a good feel for, why, if anyone is working on it, or if no one is working on it, should be back in the run mode. Let's take a few other examples. This time, not the integrity, but monitoring conditions in the PLCs. These two. First one, summarizing PLC cycle times. So PLCs and processes that these PLCs control are fairly deterministic. You kind of know what inputs trigger what actions. And so these PLCs typically have a fairly consistent cycle time for code, for executing the code. So here you can see that this is a normal PLC operation, but suddenly there's a spike. This could be a malfunction for sure, but also some malicious attacker trying to inject code. But if you don't monitor the cycle time, you'll miss this, right? Because you're not, there's no alert for this, so you have to program that alert. If you were monitoring this, then you see that in every so often this code is acting, so you can take action based on further troubleshooting, further forensics into what's going on there. Similarly, another one for trapping false negatives and false positives. Let's use another function block example here. In this, you have these conditions, several conditions, all have to be true to have this trigger bit on. But let's say all these conditions are true, but someone, some malicious attacker is forcing this trigger bit to 0. Then currently there is no way to know this. However, if you program this trap where you take this trigger bit and you have this NOT gate and then use this logic, then if someone has forced this logic to 0, then you get a 1 here, and the condition here is also 1. Then it says, hey, it's a false negative. Someone has forced this trigger bit to 0. So you don't do this for all the inputs or outputs, but you do these for critical inputs. And because this is new, this is not expected. The malicious attacker, of course, if they know about this logic, they can force on both sides, and they can make sure that you don't get this either. But it just adds another layer, right? So we talk about layers of protection. This adds one other layer of being able to understand that someone was messing with these inputs. So that's it for today, folks, for examples. Look forward to any questions.